Hello, my name's Chris Kurzik, and I'm the principal engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating. Let's begin with the outline. We will begin to talk about equipment re-rating and the issues associated with that, and allowable stresses and margins and why they're important when you're re-rating equipment. And that applies in particular to pressure vessels and to piping. And in future videos we can talk about other types of equipment like pumps and so on. Boiler Pressure Vessel Code, Section 8, Division 1 will be focus of our discussion, and Division 2. Shown on the diagram is a U2 form, a manufacturer partial data report. One of the first things we do is we source this out, including the nameplate information, and we get an idea of what year it was designed to. And one of the key reasons why we do that is, not just the rules of the addition, but also more fundamentally the allowable stresses. The following diagram is a stress strain curve typically found for mild carbon steels and for alloy steels. For stainless steels, the curves are different in higher alloy ones, but we'll talk about that because of the fundamentals here. So over here, of course, is where we begin the tensile test, where the stresses and the strain are zero. And basically the yield is defined as a 0.002 inches per inch offset, okay? And that's a definition of a yield. This yield stress is a key issue when determining allowable stresses, and the tensile stress shown here. To begin with, we'll start with the Boiler Pressure Vessel Code, the ASME one, and discuss about the allowable stresses, because as we said, determining the allowable stresses is very important when you need to re-rate equipment. So in the early editions of the code, the pressure vessel calculations for steel were performed using the ultimate tensile strength, which, the UTS or TS, and a safety factor of Fs. The equation looked like this. So where T is the thickness, the tensile stress, the R is the radius, and safety factor is shown below. Later, as the Boiler Pressure Vessel Code evolved into Section 8 Division 1, and the analysis became more in depth, the safety factor was abandoned, and the equations were rearranged, and the allowable stress was adopted. And there's sort of a roadmap in the code called UG23 and section Division 1, and it provides a roadmap to go through Section 2, Part D, and that was created. Below is an example of an equation, one of them, circumferential stresses, which is a longitudinal joint internal pressure equation. And you can see how S is now been replaced, and a few other variables have been added, like the efficiency of the weld and the thickness. The equation is more developed, And basically that's it. And you need to see codes for exceptions. Let's go through an example of safety margin, just going through the very basics so that you understand, we understand better about how this works. So traditionally they used to call it fractions, okay? And it was calculated as a fraction of the maximum pressure. Here's an example. I have a 10,000 pounds maximum pressure. I use the equation and without any factors, and my fraction or my margin is 4, for example. Okay, so this is an older pre-1999 design, and the allowable stress is with this margin is now reduced to 2,500 psi. Gee. Okay, let's look at the history of Section 8 Division 1. From 1915 to 1943, the margin was actually very conservative. It was 5. During World War II, between 1943 and 45, the margin was 4. And the details can be found in a code case 979. Later, after World War II, it reverted back to 5. And from what I understand, they reduced the margins to conserve on steel during the war because they needed to get a lot done real quick. And so they went back to the old standards again, which is 5. Later in 1951, as analysis methods improved, the margin was changed to 4. And that continued. 4 stayed around a long time, and it wasn't until 1999 addenda that the margin was changed to match. And the reason was to sort of match the European standards, and there's some more reasons as well, which I'll talk about later. I'm actually going to spend a fair bit of time on this presentation really breaking down 1999, because when we re-rate equipment, most vessels, there's a lot of equipment that's pre-1999, but nothing really older that I've seen older than 1951. But they published a report called WRC 435, and there's a lot of detail there. I'm going to spend a little bit more time talking about the 1999 change. So from 1996 to 1998, they began a study to consider changing the margin from 4 to 3.5. Okay. And as we mentioned earlier, they produced a study, and the results are shown in Bulletin 435 of the WRC, which is the Welding Research Council. And that was published in 1998. And in September, the end of the year, and they said that 3.5 was acceptable. Why did they drop that factor to 3.5? Well, it's because when they analyzed the entire history of failures, they found that the failures were due to poor notch toughness, fatigue, service degradation, like poor maintenance, and operating problems, and so on, but nothing was attributed to the design margin. They found that in the last 50 years, there was the introduction of fracture mechanics, more and more precise methods for doing analysis and design. With the age of computers, the analysis techniques have dramatically improved and more consistent. And so we have cleaner steels, and this is something I noticed in my time working in steel foundries. The toughness improved dramatically, and we noticed that when I started working, they were introducing a lot of clean methods to prevent the atmospheric contamination of steel and so on, and more controls on chemistry and so on. And so the steels were getting better and better. In fact, when we compared them against the ASTM, our steel requirements were, tensile, everything were better for during my time in the foundry and working in forging as well. And so also clean welding. Welding procedures have improved dramatically. So now we have, cleaning, very clean welding consumables made with high engineering controls. We've got great welding practices. We have very well trained people. And some of the big things is, low hydrogen electrodes to reduce the chance of cracking, and, shielding gases for, prevention of contamination, and so on. We take into account, preheats, which are pretty much necessary for everything nowadays, and interpass heat as well, for conditions like, for example, chrome moly steels, and post weld heat treatment requirements as per code, or prevention of cracking. And so there's a great deal of understanding about this. Also, the last thing is NDE advancements, especially like techniques like phased array ultrasonic techniques in the last 30 years in the age of computers. We're getting more analysis done and more efficiently done, and just like really, really high quality results. And all of these together have really improved the design. And that's why the factors have reduced. Comparison pre-1999 and post-99. The reason why we're spending a lot of time on that is most of the time when you rerate a vessel, this pre-1999, post-1999 will be an issue, because as we see in the earlier presentations, it's been a long time since there was any major changes. So basically, in a summary, you take the tensiles at room temperature and an operating, and the yield at room temperature and operating. And you can see here pre 1999 addenda, it was 1/4. That was the fraction, and then it was changed for this case. And you take the minimum of it. So you're going to start to see that the tensile will be more of an issue when you take the minimums, and the yields didn't change. Another interesting fact with this is to point out is the hydro testing. In the 1999 addenda, hydro test was reduced from 1.5 to 1.3 to provide a margin of safety during the testing, because as we recall, we dropped from 4 to 3.5. And so that's the requirement for that. Let's move on to Division 2. This is a comparison chart, a very high level. There's a lot of exceptions and things, but generally speaking, Division 1 applies to all pressures greater than 15 pounds PSIG of pressure, whereas Division 2 is sort of recommended for 3,000 and 1,000 10,000 PSIG, high pressure type units. And of course, Division 3 is even greater than that. And this is where your wall thickness is a big deal, because your pressures are so high that Division 2 has better value for higher pressures, because all of the materials that you can save on the construction, the welding, and the potential problems. So I'm a big fan of Division 2. And unfortunately, I see some of our clients that are shy away from Division 2, but there's great value in using Division 2, especially at high pressures. Now, question is, can we use some of the rules for Division 2 for Division 1? Of course we can. Like the NDE section 3, it's something that can be used for cases. And as long as, so anyway, so I'll continue. So wall thickness for Division 2, as I said, is thinner, and there's more analysis done, and that's because of modern tools. Okay, so division and better NDE and so on. And so Division 2 is more extensive than Division 1. Now, the theory for Division 1 is the maximum principal stress theory. And beginning in 2007 edition, they started using von Mises for Division 2. Now, 1968, Division 2 was introduced, and it had a design margin of 3.0 for the UTS value, and or the tensile value. And basically, you can see that way back in 68, Division 1 had 4. So they were seeking less wall thicknesses. So in 2017, there was a big change to add more flexibility. They created a Class 1 and 2 were introduced. Class 1 allowed for a margin of 3, so basically no change. And except there might be, I think there was a few details you have to be careful. And Division 2, they allowed, or sorry, Class 2, they allowed even a bigger drop to 2.4 of the tensile. There's a few things, there are a lot of different rules, very detailed rules, differences between Division 1, 2, hydrotest stresses. There's no specific limitation, whereas hydrotest calculations are mandatory for the calculation. And penetration nozzle wells, you can get away in Division 1 with partial penetration nozzle wells. For myself, that's rare. We tend to always do that for pressure wells anyways. And Division 2, it's absolutely mandatory. In 2017, as we mentioned earlier, there was a new adoption for Division 2. It was a Class 1, which is more conservative than the Class 2. And if you want to know the details, you go into Code Case 2891, and we'll talk more about the Class 1 details and Class 2. Basically, the differences you can see there is this is for the ultimate tensile stress at design and temperature. Those are the differences. But note also that the level of responsibility increases, whereas Division Class 1, no P-inch stamp is required by that standard. But you also have to look at the jurisdiction you're in as well. Whereas Class 2, because you're really getting tight on your design, they require a P-inch stamp. I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos, and we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.